Please settle down. Okay. Welcome to this lecture. So, in this lecture, we will look at some applications of heat transfer related to microelectronics and battery thermal management. So, I would like to start with what we all see in our daily lives. So, we all deal with various kinds of computing systems, right? You have laptops, smartphones, right? And all these are powered by various configurations of microprocessors. So these are our daily use devices, but then there are also devices that we don't see. These are data centers. These are large computing systems, okay, and they are using a different class of processors, okay. So this is all in the current day and time, but how have we reached here? So we can trace back the development of these computing systems to as far back as mechanical computers in the 1600s and the 1800s, then leading to punch card based devices, okay, which became very popular, and IBM commercialized them in the 1950s and 60s. And then the next tranche of development we can relate to relay based computers, which were electromechanical based around the Second World War. And Second World War time also saw development of these large relay based systems, okay, where eventually relays were replaced with the vacuum tubes, okay. But then the major breakthrough comes in the form of invention of the point contact transistor in 1947, okay, and that leads eventually to the development of the integrated circuit. So transistors were initially connected with individual wires, but then it was realized that this is not feasible, and then somebody figured out that okay, we can integrate all the components of a microelectronic system on a single silicon wafer, okay. And from here the development of microelectronics starts. So initially the cost of all these devices was very high, but then the defense and aerospace programs of United States helped to scale up the production, leading up to the first microprocessors in 1971, Intel 4004. This is the first microprocessor, okay. Around the same time, Gordon Moore, you may have heard his name, Moore's law. So he made a prediction in a short article that as time progresses, we would be able to integrate more and more transistors and at lesser and lesser cost in a given chip, and this was his prediction. And what happened was that the microelectronics industry took it up as a challenge, and it became a self-fulfilling prophecy, okay. And here is what we have seen in the last many decades. So here is your first commercial microprocessor, Intel 4004, with just 2300 transistors, and this data is not updated. This is up to 2018, but even in 2018 we have processors with a few billion transistors, okay. And this has all been made possible through miniaturization. So here what you see is a schematic of a transistor, okay, and this is the gate configuration. So here the gate is around 1 micron in 1974. By 2005 it reduced to 35 nanometers, and after 2020 we are seeing length scales of the order of 10 nanometers, okay. So but all this has to be powered up somehow. In the mobile computing devices, it has to be powered up by batteries, and at the same time whatever heat is getting generated, that has to be also safely dissipated. So here we talk about the thermal design power of a device. So thermal design power means that it is the maximum sustained power that a microchip can dissipate without violating the limits of junction temperature. So junction temperature is the temperature of each individual transistor junction, right, and there is a upper limit of temperature beyond which these transistors will not be able to operate. They will not be able to switch between 1 and 0 state, right, and there will be some degradation of physical degradation of the material. In addition to that, we also worry about the non-uniformity of heat dissipation. So if this is a microprocessor, so this is an IR image of a real microprocessor, and you can see that some areas are blue, some are yellow, and there are also some red spots. So red means high temperature, okay, and this is a distribution of the temperature, and you can see that there are small hot spots in a processor, and the thermal management needs to take care of not only what is the total heat being dissipated, but what is the distribution of that heat dissipation, okay, because let's say if you have, let me go back, can I go back somehow? Okay, yeah. So if you, let's say if you design for average heat flux, then you may miss the temperature hotspot here, okay. Okay, so this is a typical cross section of a semiconductor device. At the bottom you have the transistor layer, and these are the interconnect layers, how these transistors are connected, right. So now why do we worry so much about thermal management? So in the semiconductor devices, as the temperature rises, like a typical chemical reaction, as you would have seen in thermal management lectures in the course for batteries, new chemical reactions and physical mechanisms will trigger, okay. So for example, if the temperature of the device is high, it can lead to electromigrations. So the interconnects between the microprocessors, so there electrons can migrate and they can physically start displacing the atoms, and that can eventually lead to a loss of contact in a interconnect, and the processor can stop working. Similarly, there can be thermomechanical stresses developed due to repeated cycling of high and low temperature, and that thermal stress can lead to delamination of different layers if the cycle amplitude is large, okay. Then there are also gradual wear outs of the gate material, like a prolonged exposure to high temperature, and there are a host of other mechanisms also, right. So electronic engineers always worry about this. So as thermal engineers, we have to take care that the temperature of the device is below the specified temperature limit during the lifetime of the microprocessor, okay. Now as I mentioned, all these computing devices have to be powered somehow. So data centers, they have the continuous supply, but mobile devices like the laptops and the smartphones that you are carrying, they are powered by the lithium-ion batteries, and you would have seen a lot of discussion in this course, and I don't think I need to spend time on this part, okay. So this working principle would also be very clear to you, and the adverse effects you would have already seen in Dr. Ankur's lectures, okay. So I'll skip this part. So now I'll come to a few strategies of thermal management that are applicable to both the microelectronics as well as the batteries, okay. So overall, we can think of that in heat transfer, what we are trying to do, we are going to use a fluid that carries away the heat to the ultimate heat sink while keeping the temperature of the device within a certain limit, and we can make an overall distinction. So one major distinction that we can make is single phase cooling and phase change cooling. So by single phase, we mean that the coolant fluid is not undergoing any phase change, okay, and in phase change, it is going to undergo some kind of phase change, right, either it can be boiling or evaporation and so on. So let us look at first single phase cooling. So what are the coolants that we can very intuitively think of? Air and water, right. So this slide is somehow not coming up. So let me think of why one would prefer air and why one would prefer water as the coolant, right. So whenever we think about batteries and electronics, water is not compatible, right. But if we provide sufficient sealing for the flow of water, then water can also be used. But why would one prefer water over air in certain situations, right? So if you compare the density, the specific heat of air and water, so what you will find is that per unit volume, flow, heat capacity of air to that of water, that has a ratio of approximately 1 over 4000. So per unit volume of flow, per unit meter cube per second of flow, water can absorb 4000 times more heat, right, at for the similar temperature rise, right. So why I am talking about per unit volume? So any coolant that has to be circulated to cool the batteries or the microelectronics, that has to be pumped in some way, right, and that pump is going to require its own power, right, and that is a drain on the overall system. And how do we calculate the pumping power? It's the pressure drop in the system multiplied by the flow rate, right. So as a thermal engineer, I also need to worry about how much pumping power I am ready to spend to circulate the coolant through my device, right. So I would like to keep the pumping power as low as possible for a given level of heat flux that I want to dissipate. And if a coolant fluid can carry away more heat per unit flow rate, that is better, okay. So cooling with water, it's not new. Proof of concept has been demonstrated more than 40 years back. So this is a very seminal paper on microchannel heat sinks cooled with the liquid water. So here you have small microchannels, okay, and water is flowing through it. There is heat flux coming from below, and that heat flux can be dissipated by the water flow, okay. Now one question that you can think of is why we need microchannels, okay. So as we are miniaturizing the devices, right, so as I mentioned, the electronic devices are getting miniaturized, right, at the same time your fluid systems are also getting miniaturized to keep pace with the electronics, right. So the heat sink, as the microprocessor starts to become small in terms of the area that it occupies, I also want a small heat sink there to be accommodated over the processor, right. So now at those small length scales, as the fluid flow gets miniaturized, turbulence becomes unavailable to us, right. So we are stuck with laminar flow, okay. So now I can generate turbulence at small length scales also, but that would require immense pumping power, which is not feasible in terms of practical usage, okay. So how to increase or how to maximize the heat flux while staying in laminar flow? So you would know that for laminar flow in a closed duct, the Nusselt number is a constant. That is, it is not a function of the Reynolds number. So whatever flow rate is there, as long as you are in the laminar flow, the Nusselt number will stay constant, okay. So now Nusselt number is H d by k is a constant, right. So here H is your heat transfer coefficient, D is your hydraulic diameter, and K is the thermal conductivity of the fluid, right. So this means that my heat transfer coefficient is inversely proportional to the hydraulic diameter. So if I reduce the hydraulic diameter, I can increase the heat transfer coefficient, right. This we know from undergraduate heat transfer, right. So that's why I would want my coolant to flow through small microchannels which have small hydraulic diameter, so as to lift up the heat transfer coefficient that is available for heat transfer, okay. And if the heat transfer coefficient is high, then the same heat flux can be dissipated while keeping the temperature of the device low, okay. So that is why you have the you see the use of microchannel heat sinks, okay. So when we talk about microchannel heat sinks, so overall what will be the architecture? You will have a duct that is bringing in the coolant is distributed through the microchannels, and then the hot fluid goes out, right. But here it brings up another technical challenge, that how the flow is getting distributed in different microchannels. You would want the flow to be equally distributed, but because of the nature of flow, the flow distribution is non-uniform. So here this curve indicates uniform distribution of flow. So here the normalized flow rate is plotted with the microchannel number. So instead of a uniform distribution, you have non-uniform flow distribution with less flow near the center of the channel, near the center of the microchannel array, and more flow towards the boundaries, okay. So this is not ideal, right. So here then what is done is that you change the configuration of the inlet and outlet ducts. You make the inlet ducts converging, the outlet ducts diverging, and then the flow distribution starts to come close to the uniform distribution, okay. And this methodology is now applied over in many thermal applications, okay. Now if I am forcing a viscous fluid like water to flow through microchannels, there is going to be large pressure drop, right. So how can I minimize that pressure drop, okay. So as I mentioned, flow of water through microchannels has been demonstrated 40 years back, right, but the pressure drop is large in such a architecture. So what can I do there? So here another innovation comes in, that is that in the traditional microchannel, the fluid enters, traverses the entire length of the microchannel, then flows out. But what we can do is that we let the fluid come in, but then we divide the fluid into multiple streams, and each stream traverses only a small distance of the channel, and then it comes out. So the flow length in the microchannel gets limited, and this significantly reduces the pressure drop, okay. So this is a schematic of how it can be done, but in reality this is the architecture. So here you see two layers of channels. One is this, so here the heat flux is coming like this. So this is the first layer of microchannels, and this is a layer of mini channels. So these are not microchannels, these are ducts of millimetric dimension. Here the microchannels will be of the dimension of, let's say, 100, 200 micrometers, but these will be of the order of, let's say, a millimeter or so. So what these ducts are doing is that these ducts are distributing the liquid in the microchannels. So if you see here, the liquid is coming in, and then it is distributing in or towards both sides, dividing into two streams. It is flowing a small distance and then coming out. So you have alternative inlet and outlet ducts here. This becomes more clear here. You have the inlet duct, this you have the outlet duct. The fluid comes in, flows into the microchannel, traverses this small distance and comes out, okay. So this configuration is called as manifold microchannel heat sink. So this is the manifold and these are the microchannels, and this configuration achieves high heat transfer efficiency and low pressure drop. So you get the best of both the worlds. Okay. And another thing that helps in improving the heat transfer efficiency is that if you look here, the liquid is coming down and impinging into the channel. So this forms a configuration of a impinging jet. So you get the benefit of impinging jet heat transfer, you get the benefit of flow through the microchannel, and because the flow length is minimized, it reduces the pressure drop, overall pressure drop. So the pressure drop is lowered, heat transfer is improved, and that is what any thermal engineer would be looking for. Okay. So this is just a electron micrograph of a realistic configuration. So here what you see is this is the manifold layer, and this is the microchannel layer. Okay, and this is a cut cross section of this device. So what has been done here is the microchannel layer has been formed in silicon, and the manifold layer is also formed in silicon, and these are bonded together, and so you have a continuous liquid path. So here I hope you understand that here we are looking at the side wall of the microchannel. So the flow comes like this, it traverses like this and goes up. Clear? Okay. Okay. Now, as I mentioned earlier, that at the small length scale we are stuck with laminar flow. Okay. So one option to increasing the heat transfer efficiency in case of laminar flow is to reduce the hydraulic diameter. Another thing that we can do is introduce some instability in the flow. Okay. So for that we utilize the principles of flow instability in case of flow over bluff bodies. So here you see flow over a cylinder at different Reynolds numbers. So here the Reynolds number is less than 4, you increase the Reynolds number slightly. So at small Reynolds number the streamlines are nicely following the profile of the cylinder. At slightly higher Reynolds numbers you start getting some flow separation, right, and you have this vortex formation. But when the Reynolds number goes above 40, these vortices start to shed, and then you have a vortex shedding which is periodic in nature. Now this vortex shedding can be utilized to increase heat transfer, and how we can do that? Okay, this is a schematic showing the vortex shedding from a cylinder. Okay, so here is a description of a heat sink where there are no micro channels, but there is a forest of these small micro pin fins. The flow is entering from one side, exiting from the other side, so it is flowing, let us say, into the plane of the board through these for micro pin fin arrays. These are called as micro pin fins. Okay, and you can have different arrangement of these pin fins realizing different levels of efficiency. So here you see a plot of pressure drop versus Reynolds number. So up to a certain Reynolds number the plot has a linear profile which is expected for any laminar flow, but after a certain Reynolds number the profile changes. Why is that happening? So beyond this Reynolds number vortex shedding is starting, and that is causing the flow to become unstable. Okay, so if we look forward, so here are the streamlines of flow when the Reynolds number is small, and you can see here in between these micro pin fins the flow behaves as if it is flowing through a micro channel, and in these between these pairs of micro pin fins you have these recirculation zones. Okay, but as you increase the flow these recirculation zones become unstable and they start to get oscillated like this, and they start to disturb this flow also, and that leads to a continuous vortex shedding, and that improves the heat transfer. So here this is a temporal map of the velocity profile along these three lines. So like here if you see these three curves, the velocity profiles are changing as we are proceeding in time, and they keep on switching between each other. Okay, so the flow, essentially the flow looks like this. It starts to carry away some of these recirculation zones, and let's see if this video plays. Maybe I can come out of the, okay, let me see. Okay, unfortunately the video is not playing. Yeah. Anyway, so what you would see here is a flow that is oscillating laterally. Okay. So in single phase flow, you can do lot of things to improve the heat transfer, okay, by introducing certain instabilities or reducing the overall length scale of the flow. How I am doing in terms of time? Okay, we have time. Okay, so any questions so far? Yes. Yes, in that case the vortex shedding will be more, but the pressure drop will also be high. So then you have to take a call in terms of the trade-off. That are you, for the increased pressure drop penalty, are you getting a higher increase in the heat transfer?
Just a little bit.
Yeah, there are many different configurations that have been tried of even the staggered pin fins also. Even the profiles of these pin fins have been looked at, whether these should be cylindrical or oval in shape, right? So many things have been looked at in this. Okay, but overall this kind of configuration is able to provide more heat transfer for a given pressure drop when compared to microchannel configuration. The disadvantage is that this is a bit more difficult to fabricate at the small scale. Okay, fine. Sorry. So by pressure drop I mean flow is flowing from this end to this end. What is the pressure drop required to make the flow to flow through this array of pin fins? नहीं वो कैविटेशन तक नहीं जा रहे हैं ये we are far away from cavitation. Yeah, so that is not a concern here. Yeah, so we are well above the vapor pressure, so that does not happen. Any other question? Okay. Okay, so this was a brief overview of single phase cooling. Now coming to phase change cooling. Okay, so if we let the fluid change its phase, then the fluid can absorb latent heat, and so we can deal with higher heat fluxes also. So in phase change cooling, one of the devices that has been used a lot both for cooling of microprocessors and also being explored for thermal management of batteries is a heat pipe. Many of you would have already read about this in your undergrad heat transfer. So a heat pipe is basically a device to transfer phase change based heat from a heat source to heat sink. So what you have here is three zones: evaporator section, adiabatic section and condenser section. So this evaporator section is in contact with your heat dissipating device, and this condenser section is in contact with your heat sink that ejects the heat to the outer atmosphere. So there is a wick, and in this wick the liquid coolant flows through capillary pumping. I will briefly explain how this works. So this wick absorbs heat from the outer body, the liquid evaporates, it goes into this central vapor section, and the vapor flows towards the condenser section where it condenses back into the wick and the liquid coolant comes back. So there is no active pumping involved, but it is the capillary effect that passively pumps the liquid from the condenser section to the evaporator section. Okay. So this device is also not new, right? It was invented way back in the 1960s, right? But nowadays most of your laptops that you are using, they all have heat pipes of different configurations. Okay. And in the heat pipe, the working fluid can be selected based on the application, right? Many times it is just water, but it can also be some alcohol, right, depending upon the temperature range that we are looking at. And usually the space inside the heat pipe is evacuated. We remove all the non-condensable gases, and it is only the coolant and its vapors as far as possible. Okay, because any non-condensable gases inside the heat pipe will severely reduce the heat transfer efficiency. Okay, and in the wick, when we have to design the wick, there are few parameters that we take care of. One is the pore radius. Pore radius means the size of the individual pore of the wick, that decides how much capillary pumping is available for pumping of the liquid. Then the permeability of the wick, that governs that if the liquid has to flow through the wick, how much pressure drop it will experience. And then of course the thermal conductivity of the wick material. So we don't want the wick material to be made of something that is insulating, that will defeat the purpose. So it has to be made of a high thermal conductivity material. But in general, compromises are made in these three parameters to maximize the overall performance. Okay. So heat pipes can have different geometries, different kinds of wicks depending upon the application. Okay. Now there is one important aspect of heat pipes is that, let's say I have mounted the heat pipe in my laptop. Okay. In general it is working, but now you start playing some game or start doing some heavy computational simulation. The processor would work at a higher power, it will dissipate more heat, and the heat pipe has to transfer that heat from the evaporator to the condenser section. So is there a limit to which the heat pipe will work? So what do I mean by the limit? So let's say this is the heat pipe, this is the evaporator section. Can it happen that the liquid is coming back, but it is not able to come back at the same rate at which it is evaporating from the wick in the evaporator section? So if that happens, what will be the result? Here the wick will become devoid of the liquid coolant and the wick will dry up, and this is called as the dry out failure of the heat pipe. And then in that case, latent heat absorption will not be available to you, and only conduction through the heat pipe body will be available, right? And that will lead to a rise in the temperature of the device that you are trying to cool. Okay. So there are different limits to the operation of the heat pipe that have been looked at. Okay. So the first and the most important limit is the capillary limit on heat pipe. So let me briefly explain this here. So let us consider the wick. Let's say it consists of these different microstructures. I am drawing just a 3D sketch. Now if I look it from the side, it will look like this. Okay. And let's say some liquid has wet this wick. So the liquid will form meniscus in this wick like this. Okay. And say now heat is coming from below. Now what will happen? This liquid will absorb this heat and it will start to evaporate. Okay. So, liquid is evaporating, but it is also flowing along the wick. Okay. So, it is flowing in this direction through these array of channels of pillars. Okay. So, the result will be that towards the far end of this wick, the curvature of the meniscus will be high, and at the upstream end the curvature will be low. Okay. So, what does this mean? If we recall Laplace pressure, so Laplace pressure difference is for any spherical curvature is 2 sigma by r, where r is the radius of curvature, and here the radius of curvature is small, here the radius of curvature is large, right. So, this means that here the liquid pressure PL, let us say this is 2, this is PL1. So, PL2 is less than PL1, right, and so there is a pressure gradient, and so this pressure gradient is going to drive the liquid flow in this direction, and this is called as your capillary pumping pressure, whatever that net pressure difference is. Okay. Now, capillary pumping pressure, the job of the capillary pumping pressure is to suck the liquid through the wick from the condenser end to the evaporator end. Okay, and that is the maximum driving force that is available for the flow, for the working of the heat pipe. Now, this capillary pumping pressure delta Pc, it has to work against 3 pressure drops. First is the pressure drop of the liquid as it flows through the wick, then the pressure drop of the vapor as it flows through the center section, and then any gravity related pressure drop if the depending upon the orientation of the heat pipe, if the heat pipe is large in dimensions. Now, the heat pipe will work properly, that is the wick will not dry out at the evaporator section as long as the capillary pumping pressure is greater than the sum of these 3. Okay. Now, as I keep on inputting more and more heat, delta PL will keep on increasing because the liquid flow is increasing. Okay. And eventually what will happen is that this sum will become larger than this, and so at that point the liquid will not be able to compensate for the evaporation and the wick will dry out, and this is called as the capillary limit on heat pipe operation. So, any heat pipe that is being used for thermal management of microprocessor or any battery pack, a capillary limit will be specified, that is beyond which the heat pipe will not work, its wick will dry out. Okay. So, this is the most important limit on heat pipe operation, but there are some few other limits that have also been identified which can sometimes manifest based upon the design of the heat pipe. For example, there is a boiling limit on heat pipe operation, right. So, let us say I have a wick of the heat pipe and at some location boiling starts, right. So, what will happen? Some bubbles will start to form. Now, in conventional pool boiling, the bubbles can come out of the liquid, but here the bubbles can get trapped in the wick and those bubbles can then block the flow of the liquid, and that is called as the boiling limit. So, if this also happens, then again the wick will dry out, okay, sufficient liquid will not be able to reach, right. And then there are also a few other limits like sonic limit, that is how fast the vapor can flow. The maximum speed at which the vapor can flow is the speed of sound, right. Similarly, there are few other limits which I will not go into the detail, but what essentially I want to say here is that these limits, at what operating temperature these limits arise, that depends upon the design of the heat pipe. Usually the capillary limit is the first to reach, and so that is why it is the most commonly talked about, but in certain situations other limits can occur, and then the designer of the heat pipe has to be careful about when, at what operating temperature these limits will be reached, because any such limit will diminish the performance of the heat pipe. Okay. Okay. So now, in case of large static systems like your desktop or servers, you will not require these heat pipes. They are mainly for mobile devices, right? So, for example, here this is a schematic of how the heat flux dissipation in smartphones has increased over the years, right? But at the same time, the thickness of the smartphone has reduced, right? So, right now the thickness has seemed to be stabilized, but 6-7 years back there was a lot of competition between different OEMs and how much thin I can make the phone and how fast the phone is. Now this is a dual challenge for a thermal engineer. You have lesser and lesser space available to dissipate more and more heat, right? So there then comes how to design such very thin heat pipes that can operate in such small space. So here you have different configurations of the very thin heat pipes being implemented in laptops, in smartphones, in smart watches. Okay, and overall, as a thumb rule, if you see in the literature, the heat dissipation of the processor in a laptop is around 20 watts, and that in the case of a smartphone is around 5 watts. Now the processor designers are trying to bring this down even further, but whatever that is, heat is, that has to be dissipated. So here we come across another counterpart of the heat pipe. It's called as the vapor chamber. So vapor chamber is same as the heat pipe. The only difference is that in the heat pipe, the evaporator and the condenser were separated by a certain distance. In the case of vapor chamber, the evaporator and the condenser are directly facing each other, and this vapor chamber can then dissipate heat in the z direction. And in some of the smartphones now, this configuration of the vapor chambers is being implemented. Here it is showing how thin a vapor chamber can be. About, I think, 2-3 years back, Samsung had advertised that okay, the phones are liquid cooled. Now there the liquid cooling was referring to the introduction of the vapor chamber in the heat pipe. So what the vapor chamber is doing is that in the smartphone, the processor is occupying a small area. The job of the vapor chamber is to spread that heat over the larger area so that it can be dissipated through the back surface of the smartphone to the outer atmosphere, thus maintaining the processor in its safe operating limit. And inside this vapor chamber, on one surface you will have the evaporator, and on the opposing surface you have the condenser with its own wick architecture. Okay. So here is just a picture of realistic heat pipes, how they are being implemented in the laptops. For example, here you have the two evaporator sections, and then here this is connected to a condenser and then to the heat sink, because in the laptop, the, let's say your processor is somewhere here, right, but the fan is somewhere here. So then the job of the heat pipe would be to carry the heat from here to the heat sink that is connected to the fan. Okay. So there are many existing challenges in ultra thin heat pipes. Okay. So the one of the really interesting and yet unsolved challenges, how to make flexible ultra thin heat pipes. So you would have heard this word of flexible electronics, right? Very thin smartwatches, right? So for that, and also in biomedical applications, Internet of Things, you need flexible electronics. So can we, or do we need certain very thin heat pipes or vapor chambers which are also flexible? But for flexibility, you need to use polymeric materials, but polymers have low thermal conductivity. So work needs to be done to design new materials for these kinds of applications, right, where flexible heat pipes or vapor chambers can be developed. And this is a prime example of interdisciplinarity, where material science, fluid mechanics, heat transfer, they have to come together to design new working devices. Okay. Then I like to briefly talk about thin film evaporation. So this is fundamental to the working of all heat pipes and vapor chambers. So if we look closely, let's say if we focus on this region, okay, so this picture is a zoomed in image of this, where this part, so this is zoomed in and rotated 90 degree, okay. So here is the solid surface and there is the liquid film being formed. Now here there are three regions of the film thickness. Region 1 has the smallest film thickness, region 2 is intermediate, region 3 is large. In region 1 the film thickness is so small that the liquid molecules are strongly adsorbed to the solid surface, okay. And what happens is that here the adhesion force is so high that whatever the heat flux is, these liquid molecules will not separate and enter into the vapor phase. So here if I try to calculate the thermal resistance will be infinite. On this side, this adhesion force is small, but due to the large thickness of the liquid, you have large conduction resistance. So again here the thermal resistance is high. It is this region 2 that is the sweet spot, where the thermal resistance is small and the heat flux is high. So when we are designing any wick, new wick for heat pipes or vapor chambers, the target is to maximize this region per unit area of the device. So if this region is large, you can get high heat transfer coefficient. So this is called as the thin film region. So you want the thin film region per unit area of the device to be as large as possible, okay. And that is done through micro and nano texturing. So either you make separate wicks or you micro or nano texture the surface of the various so for example here you have the nano texture, okay. So what we see here is these are the holes. If you see the scale, the whole scale is very small. Okay, so different kind of textures can be made to try to maximize that thin film region that I was mentioning. So many research groups are working on this problem to develop new scale textures either at the micro scale or the nano scale. For example, here, went one. Like here you see, you have a micro scale, you have 20 micron texture, and on top of that you have a nano texture. Okay, so dual scale texture where it is being tried to maximize the thin film area and increase the heat transfer coefficient. Okay. Now this was one kind of phase change. So phase change for water, it can be either in the form of evaporation or the other can be boiling, right. So what is the difference between evaporation and boiling? Can somebody tell me? Now what is the physical difference in the process between evaporation and boiling? So evaporation is at the surface of the liquid air interface, boiling is at this liquid solid interface, right. So boiling, in boiling you can achieve much higher heat flux, right. So instead of evaporation, a lot of work has also gone into flow boiling. So let's say I was talking about single phase cooling where liquid is flowing in the channel. How about that as it flows through, it also undergoes boiling. Then you can absorb much higher heat flux, right? But if we all know this, but it has not yet been commercially implemented. So what are the bottlenecks there? The main issue is how the nature of flow changes in the downstream direction. So here if you see, the flow is entering, it is single phase flow, the boiling starts, okay, and then you have annular flow, and eventually the liquid layer next to the wall dries out and you have a mist flow. Now as thermal engineer, I would like to remain in this zone, but it is not so trivial to maintain the flow, the nature of flow like this, because the nature of flow is heavily dependent upon the flow rate and the overall pressure drop, right? And so a lot of control algorithms are implemented usually while dealing with flow boiling, where continuously the flow rate, the temperatures are controlled so that the flow remains in the preferred region and maintains the wetness of the walls. Okay. There can be many instabilities in this flow. For example, here liquid is coming, it is entering into these channels, boiling is happening, but perhaps when the boiling happens, the vapor starts to get accumulated near the inlet zone and it chokes the flow. The liquid is not able to enter the microchannels and eventually here you have a dry out. So flow boiling is very promising, but these bottlenecks need to be overcome. Okay. And then further, if you want to increase heat transfer, you can mix both the strategies in the form of a jet. So two-phase jet impingement, where jet is impinging on the hot surface and it's also undergoing phase change. So there you get the benefit of both the flow field of the impinging jet as well as the latent heat absorption due to boiling. But again here the challenge is how to control this phenomena so that the net overall flow always remains within our preferred type. Okay, so I will close this lecture by a short discussion on battery thermal management in EVs, the electric vehicles. Okay, so in electric vehicles, the batteries all need to be maintained right within the required temperature zone. So various strategies are being used, and the strategies that I have mentioned, all of them or a combination of these are being tried. For example, single phase cooling, you can have air cooling that is going through the battery packs. Okay, then you can have liquid cooling. So here you have the battery cells, and either these battery cells can be directly immersed in cooling oil, which is dielectric, or you can circulate water, you can have indirect cooling. So this is a schematic from one of the patents filed by Tesla many years back, and they have made this patent public. Okay, so you have here this cooling channels where liquid coolant is being used to cool the battery pack. And then other strategies can be used. For example, cabin air can be circulated through the battery pack. You can have your air conditioning system, part of which can be used for phase change cooling, where the refrigerant is circulated through the pack. You can also have a combination of heat pipes in conjunction with single phase cooling, where heat pipes, if you have the battery pack, so from within the pack, the job of the heat pipe is to transfer the heat out, from where it is then carried away by the coolant, right? You can also utilize phase change materials, where like where the any spike in the heat flux would be managed, right? So different strategies in different combinations have been utilized. So I think I'll stop here. Yeah, it's 12:31. Okay. If any questions? Yeah.
And does the working temperature for the heat pipe depend on the laser fluid which is used in it, or heat pipes are designed for different temperatures?
So the working temperature of the heat pipe will depend upon the working fluid and at what pressure it is charged in the heat pipe. So for example, water, its boiling temperature is 100 degree C, but if depending upon the pressure at which water is charged, I can achieve different working temperatures because I am changing the saturation pressure. So then the saturation temperature is also changing at the same time. Okay. So for example, if you have a pressure of around a few tens of millibars, then the saturation temperature can be brought down to 30-40 degrees or even lower also. So it all depends upon which working fluid and at what pressure it is charged in the heat pipe. Okay. Any other question? I'll need to check that. I'm not sure if it has been implemented yet. Maybe Ankur can answer. Yeah.
Certainly, at the scale of getting research, this is something that we will do. I don't think it is a product.
Yeah. Okay. Any other question? Okay.
Thank you.
Also, I know I'm present everywhere and the lab. That the amount of fluid that we get, because we said that the pressure remains that particular temperature at which the phase change takes place of the fluid inside the heat pipe.
Yes.
The quantity of fluid inside the heat pipe, does that matter when you're stating it?
Yes, it does. So the dry out heat flux will also depend upon how much fluid is there inside, and that is why whenever new heat pipe is designed, it is tested at different charging ratio. So charging ratio means the amount of the liquid added divided by the internal volume of the heat pipe. So that is also strongly a parameter.
Is it like well-known values are available, or it depends on any type of design and lot of
It is dependent upon the design also. Yeah. Generic values are not. There are a lot of values available in different academic papers, but as such general thumb rules are not.
super complicated 3-4 hours.
Yes, 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 yes. Yeah. Okay. Thank you.